student to listen to everything I just said. So, right, let's get going here. So how many of you have actually downloaded these CDF files and you're going to do interactives with me? Anyone? Yeah? No?
Going to.
Yeah? You're going to? Okay. So I don't want to repeat myself. This has all been sent out in emails, but I'm using Mathematica. We have another student. Okay, let's do this. You think we can squeeze right in the middle right there? Just do we have a chair? This ought to be fun. See if I can, who I can knock out with a chair here. You have it, sir? All right. So what is Cal 3 about? What is Cal 3 about? Anyone have any ideas? Okay, multivariable calculus. That's what it's called at some other schools, right? Just call it multivariable calculus. What we're going to do, if you look back at Cal 1 and Cal 2, everything we dealt with was pretty much coming from the idea of y being some function of x, right? Y is a function of x. And then we draw that, and Cal 1 we like to talk about, you know, what's the slope of the tangent line, and that's the derivative, right? In Cal 2 we look at the area underneath the curve. We rotate it around the x-axis maybe or something like that. We find some volumes, but pretty much mostly everything we did started from the graph of a function on a flat sheet of paper, right? Two-dimensional. That's what Cal 1 and 2 were about. Cal 3, multivariable calculus, means that you're no longer going to be dealing with y being determined by a function of x. You're actually going to have another variable, z, which is determined by some function of two variables. So instead of having one input, right, input was x, output was y, we can in this class have two inputs, two variables, two independent variables, and one dependent variable. And so the question would be, what does that look like if we graph it? We know what this looks like, right? Two-dimensional, but what does that look like? And that's going to turn out to require 3 dimensions to visualize, right? We have, back in Cal 1 and 2, you have one input means the x-axis was one dimension. We have the y was the output, right? So we have a second dimension, and we could somehow represent the graph in here on that sheet, right? But if we have 2 inputs and 1 output, then that's going to require 3 dimensions for us to visualize, isn't it? Does that make sense that that would be that way? So now you have more than one variable calculus. So we're going to go look at these things, whatever they turn out to be, and we're going to do calculus on those things. Except that the idea of a tangent line is no longer going to be sufficient because the things we're looking at are no longer curves in two-dimensional space. So we're going to spend most of our time in Cal 3 in three-dimensional space. And that's what makes, at least for me, that's what made Cal 3 the most challenging when I took the class myself, is that I can remember being in an auditorium. There's about 100 students or so in there. And I sat somewhere around 3/4 of the way back, and the board was way down there. And there's some guy drawing on a little chalkboard, drawing three-dimensional things. I'm sitting there. I've never even drawn in tried to draw anything in 3 dimensions before. And he's not very good at it. I'm not very good at it. And so we're all kind of just, our brains were more wrapped around trying to get a good drawing rather than trying to understand the calculus. So when I got into teaching myself, I said, well, when I get to this stuff, I'm going to use the technology that's available to me to be able to kind of take that aspect of it and not make it a big hang-up for us. So that's why I'm going to use the software I'm using. Everything three-dimensionally you'll be able to see, and I will rotate, and you're not going to have to draw it. That's why I provided these things to you electronically, so you can go home and rotate them and zoom in on them, and that way you're just thinking, let's do the math. Like, what's the math behind this, instead of being stuck on a flat. Trying to draw a three-dimensional space on a flat sheet of paper is not easy. All right? Okay, so Cal 3 roughly is just us getting off a flat sheet of paper and getting out into three-dimensional space. And it doesn't stop there. You can have functions that where you have something like z is equal to a function of, well, how about x, y, and not z, I won't use z, I'll use t. So now you have 3 inputs, 1 output. Does that make sense? So what would you need in order to visualize something like that? 4 dimensions. Good luck, right? That's not going to be easy. Or you could have something like this. How about z s is some function of x, y, t. So I have 3 inputs, but there corresponds to it a pair of outputs. So you plug in x, y, t, and somehow this function gives you 2 things back, a z and an s. So now you need how many dimensions to see it? 3 in, 2 out, 5. Again, what do, right? So even though 3D is going to be nice, it's still multivariable calculus really means there's no restriction on how many variables you can have. All right? Now, we won't mess around with 5-dimensional space, but we won't try and visualize it, I should say. All right. So since we're going to be dealing with 3-dimensional space, I brought 3-dimensional space in for you today. Okay? There it is right there. So this is what we're going to start today's class with. What I recommend is, while you're getting used to 3-dimensional space, you make your own 3-dimensional space, you know, out of, I've seen people do like a box. They'll use like a shoe box, something like this, right? You take a shoe box and then you just like cut sides off of it, and so you make basically like the corner of the room out of it, and that's a good way to start maybe at home. If you need it. Some people just, they get it right away. But if you need it, I would come up with something you can work with. The only reason I'm using this one is because I can put it on camera. There it is, 3-dimensional space. So you ready to start messing with 3D? Yes. Yeah? All right, let's do it. So we have coordinate system, 3D coordinate system. And I know this is going to seem kind of elementary, but in order to understand R3, 3-dimensional space, we have to be comfortable with 1-dimensional space, 2-dimensional space. So when we use this double struct capital R, we always looked at that as meaning all the real numbers, right? For all real numbers. And so a number line was what we could use to represent that, 0, everything both directions. But what was up here was like a 1. It was raised to the first power, and that's R1. So R1 are all the points on the number line. If I tell you to describe to me what is x equals 4, what would x equals 4 be in R1? A point, isn't it? It's a point on that line. So I could just move. I don't think I'd go out to 4, but I just move it out. I don't go that far, but go out to 4, and we have a point, right? So this is a point in R. What we're going to see is that this same equation in R2 is not a point. And this same equation in R3 is not a point. So that's why we're talking about it. Everyone with me, though? R1, x equals 4, that's a point in the space. Now, if we move to R2, right, that's 2-dimensional space now. So we use this double struct R2 like that. Then the idea is that we have all the numbers, right, all real numbers, and then another set of all real numbers. So that creates our perpendicular number lines, right? This is a number line. This is a number line. So we just put them like this. That's R2. So I hope we're all comfortable with what an ordered pair is, right? Ordered pair, 5, 2, something like that. That just means you move on the x-axis 5. I better change that. I only go out. Let's go 1, 1, 2. All right, means over 1, up 2. Come on, this can't be what Cal 3 is about, right? I mean, this. Don't worry. It'll get a little more interesting. All right, so that right here, this right here represents what in R2? A point, right? This is a point in R2. This is a point. Now let's look at this. What is x equals 1? So if I walk in here, right, let's say next class, and I say, everybody, what does x equals 1 represent geometrically? What should you answer? What should your answer to me be, or what should your question back to me be?
On the x-axis.
If I just say, what does x equal 1 look like? That's all I tell you.
Is it in one dimension?
You need to ask me what dimensional space I'm talking about, right? In R1, this is a what? Point, right? But in R2, x being 1 means it can be any point in this space as long as the x-coordinate is 1, right? So this would include in it the set of all points that have an x-coordinate of 1, right? So it's the set of all ordered pairs such that x is 1, right? Have you all seen this notation before? The set of all ordered pairs, 1y, such that y is an element of R. So let's see if that all makes sense to you. The equation x equals 1 in the space R2 is all ordered pairs, all points in the space where your x-coordinate is 1, your y-coordinate is y, and y can be what? Any number. So that means it can be this point, this point, this point, this point, this point, all of them, right? So you put them all together and you get a vertical line. Yeah? Compare that to y equals 0. What is y equals 0? Let's say we're in R2, right? We're still in R2. So this would be horizontal line, right? Going through y equals 0. So it's actually the x-axis, isn't it? Okay. Got it? So this is going back and showing you that same thing. If we write down in two-dimensional space, in R2, x equals a constant, I'm going to use c for constant, is going to be a vertical line, and the y value is what we call free. Y is what we refer to as a free variable. So your x is fixed, but your y is free to be whatever you want, and that gives you your vertical line. If you have y equals a constant, this is horizontal, right? And this time x is free. That's what's happening in R2, horizontal line. If there are no questions, I'll continue. Some other lines that we should be familiar with. I mean, these are just basic lines from college algebra. Let me make these a little bigger. Y equals x. There's a special name for this special relationship, this line. What is this line called? Y equals x. Anyone remember what it's called? What? It is a parent function, but it's it has a special name. Like
Slope?
It has a slope of 1, right?
Yeah.
No? The identity. This is the identity function. This is the function y equals f of x equals x. They call it the identity because if you look at this as a function, whatever you plug in is what comes out. So it's identical to, your input and output are identical. the thing that was important with the identity back in college algebra and even in like pre-cal and calculus is that, remember if you have a function, if it's 1-to-1, that means it has an inverse. And the inverse is always the reflection of the original function over the identity. That was part of what made it important. But 3x is another function. It's not called the identity, but it just has a different slope. And the important thing I want you to see here is that if you're given the function or an equation y equals 3x, every ordered pair on this, right, has to follow that formula. The x coordinate is x, the y coordinate is 3x. Yeah? Negative slope. All right, 3D, let's do it. So what we're going to do is we're going to imagine that we have our standard two-dimensional space, our x-axis and our y-axis. And we're going to create a third number line, which is going to, well, we don't really have anywhere to put it, so we're going to make it go right through the center, right? It's going to punch through this page and come out the other side, yes? And that will be three-dimensional space. So we'll have an x-axis, a y-axis, and a z-axis, and that's what we call R3. So when we have a point in R3, it's going to be not an ordered pair. We're going to call it something else. Anyone know what we call? Ordered triple. That's exactly what it's called. It's an ordered triple. So if you give me a couple of numbers, plug them in there, I should be able to represent that as a point in this three-dimensional space. So let's go with 3, 5, 2. How about that? 3, 5, 2. Ordered triple. So how would I graph that? I would go out 3 on the x-axis, yes? I would go up 5 on the y. 1, 2, 3, 4, 5. So I'd be here. So something like this. I'm just drawing these as a guide. And then on the z-axis, I need to go 2, which should come out at us. 2 units or in? I guess it would depend on how you decided to put this axis. Are you calling this positive or are you calling that positive? And it turns out that you could choose either way, and that's a problem because if you're doing your math with your z-axis coming out this way and you're doing yours with your z-axis going in, then your math's not going to be the same. Okay? So we have to agree on how we're going to do it. And it's called the right-hand rule, and I'll show it to you in a minute. But because you don't know that yet, I'm just going to tell you that z is coming out towards us positive. All right? So I'm going to just move 2 units along this, and I have a point sitting out here. Yes? Can you draw that on your piece of paper? No, it's not very easy, is it? Right? So let me erase this. And here we go to 3D. So I'm going to pop this out of two-dimensional space. There it is in three-dimensional. Come on. Okay. Everyone see that? So now your sheet of paper, right, your old one, we laid it down on the ground and we kind of turned it a little bit. Y'all see it? So x is coming out positive this way, y is positive this way, z is positive up. Now when you look at my graphs in class, I want you to pay attention. Wherever the x is labeled, that's the positive direction, right? Sometimes these numbers won't be there, so just as long as we all understand that the x is the positive direction, this y is the positive direction on the y-axis, the z is the positive z. So now let me go ahead and move, what was it, x was 3. And then y was 5. And z was 2. And so just to show you some of the things you could do on this, if you were to get this at home, you could zoom in on this. You hold down the control key, and then you just kind of go in like that. And then if you hold down the shift key, no, it's not shift. No, which one is it? Oh, there it is. Shift key, you can move it left and right. So can you all see this? I came out on the x-axis 3, the y-axis 5, z-axis was up 1. Do y'all see that?
Up 1 or up 2?
2, sorry, 2. Now, I'd like for you to get out this sheet of paper, because you can graph that on this sheet of paper. Try and do it yourself. Try and graph 3, 5, 2. While you're doing that, I will do it up here. This graph paper can be found on our website, okay? On Canvas, under Files, I have 3D graph paper up there. You can print off copies if you need to. Now, you won't always have 3D graph paper, all right? So let me show you how to draw 3D space a little bit, give you a hint. Draw a vertical line, create your origin, and then what you do is you want to draw a flattened out X, okay? A squashed X. You do not want to draw this, okay? That is a very difficult three-dimensional space to draw on. Do y'all see the difference between these two? Which one of these looks more like 3D to you? Left or right? The right, I hope it does. I mean, this one is very hard to draw on because what happens is it's almost like you're looking from the top and it's hard to distinguish things. So X is here, Y is here, Z is here. Notice that all those lighter lines, notice that they're all parallel to the axes. So you have like an entire set of lines that run parallel to the x-axis. You have an entire set of lines that run parallel to the y-axis. And you have another set of lines that run parallel to the z-axis. Do you see those? And so when you're moving along in here, on the x-axis, if you want to go out 3, you just go 1, 2, 3. Let's just draw a reference point for now. And then if you want to go the y-axis, you want to move, how many, 5? You move along parallel to the y-axis, 1, 2, 3, 4, 5. And then z is 2, so you just move up 1, 2. I think yours should be easier to do than mine. So up 2, and you draw a point. That is the point in three-dimensional space. Were y'all able to get yours on there? Anyone have any problems with it? You're okay? Okay, try and draw this one on your sheet of paper. Try and draw -2, -1, -3. Put that point on there. And after you finish that one, do the point -1, 0, 4. Y'all getting the idea here? Yes? Trust me, there's calculus in here, okay? It's coming. But you got to be able to walk around in this space before you can do anything in it, right? And if we assume you can plot a point and you can't, then you're in trouble to start, right? Well, guess what? If you got, who has all 3? No? Not yet? If you have all 3, connect them together. And now you've drawn a triangle in three-dimensional space, right? If you need a hand, just raise your hand. I'll come by and I'll help you. Oh, did you get one of these? Do you want to use one of these?
Oh yeah, I got one.
You did? Okay, you just trying to do it on your own?
Yeah, I just
Yeah.
wanna-
I would recommend you try and do this on your own. I mean, the graph paper's there as a guide to start us out, but you should be trying to do it on your own at some point. You'll get good with it if you just practice, like anything else. All right, can I move on? Y'all need more time to draw these points? Everyone's so quiet, I'm not sure if that's good or bad. I'm used to it though, right? My old Cal 2 students, I'm used to it. I'm kidding. So I want to show you on this point that everyone has, hopefully on their sheet of paper. It's very difficult without these reference dotted lines to tell where that point is, right? Just from different perspectives, it could be in different places. So those dotted lines kind of help us see it. How far away from the, like there's the ground, right? The ground is like the XY, flat sheet of paper on the ground. How far away from that is that point? 2 units? Because that's how high up it is, right? So the ground, that thing, the XY that we're used to, we're going to start calling that the XY plane. It's a plane, it's a flat sheet of paper. The XY plane is the ground here, right? Then we also have what we're going to call the, there it is, the YZ plane. So the YZ plane would be the plane that cuts through the Z and the Y axis. So it's like a sheet of paper here. It's like a wall, isn't it? The YZ plane. How far away from that point, from the YZ plane is that point? 3 units, because we came out 3 along the x-axis, right? How far away from the XZ plane would that be? 5 units. So the XZ plane is like this wall on this side. Yeah? Agreed? How far away from the y-axis? What is the shortest distance between this point and the y-axis? How would you get that? Do y'all see it? It goes from here to that point right there. And you could draw, this would be a right triangle, wouldn't it? Do y'all see that? Not a very good angle here. And so what, give me the dimensions of that right triangle. Like what's this side? 2. And what's this? 3. And so you could get that, right? Pythagorean identity? Okay. So we do know the shortest distance between that point and the y-axis. Do you know the shortest distance between that point and the x-axis? That'd go here down to that corner, wouldn't it? And so you could set up another triangle, do the same thing. Shortest distance between this point and the z-axis would go from here to here, yeah? And you could set up a triangle that looks like this. Do y'all see these things? Okay. Those are all going to be homework problems. You're going to have a point. They're going to ask you shortest distance between that point and these planes. And all right, let's proceed. The right-hand rule. Took a picture of my hand and put it up here for you. There you go. Right-hand rule says what? You use your right hand as the guide. Your z-axis is always, the z-positive is always your thumb. Your fingers on your right hand should curl from the positive x to the positive y. So here we go. If this is how I'm going to draw my 3-dimensional space, my thumb is z. That has to be positive x. I can't label it any other way. And this one has to be positive y, so that my fingers curl from positive x to positive y. Got it? If everyone follows the right-hand rule, then all of our 3-dimensional spaces, the mathematics in those spaces will match. Because it is possible to draw it in a way that yours and mine are different. All right? How many of you have seen that rule before? Physics, right? You kind of have to have it, right? That has to do with like torque and stuff, right?
Electromagnetics.
Yeah. So there's all sorts of different things we use for that. All right. Well, if you remember back in R2, two-dimensional space, and this would be in pre-cal, we started to talk about angles and all this stuff, and it became very useful for us to label these four quadrants, right? Quad meaning four. And why did we go counterclockwise? Why didn't we just go 1, 2, 3, 4, or like 1, 2, 3, 4 go clockwise? Why did we go counterclockwise? Just for fun? No. Yeah, because we always started our angle at 0, pointing out the x-axis positive, right? Then as the angle gets bigger, we go counterclockwise, right? So our angle got bigger, bigger, and then came around. So we wanted it so that your first angles, your smallest ones, would be in quadrant 1, and then you'd very smoothly proceed into quadrant 2, and then 3, and then 4. It wouldn't make sense to do it another way, right? If that's the way you're going to refer to angles. So that's why we did it. Well, if we're in three-dimensional space now, you're going to have 8 sections that are separated by these, what are we going to call them? Let's see. These we called the coordinate axes, right? These axes created 4 quadrants. Something is going to create 8 things for us here. So what's going to separate these 8 sections? How about the plane, the ground? Okay. How about everything above the ground coming out at us from this wall and out from this wall? Do y'all see that? If not, this is it. It's everything in here. Do you see it? That's what we call the first octant. And in the first octant, we'll just call it O1. Your x must be positive, your y must be positive, and your z must be positive. Agreed? Your order triple, all the points that live in here, all the numbers that you plug in the order triple must all be positive numbers. There you would be in octant 1. Now where's octant 2? Where do you think? Below it? But where do you think? I guess we could have done anything with this. What the convention that we used is that looking at it from the top, remember if we're looking at it from the top, right? Z's coming out at us. This was quadrant 1 in pre-cal. If that's going to be octant 1, then quadrant 2 is here. That's where we're going to make octant 2. Then octant 3, octant 4, and then when we go to octant 5, we're going to go below octant 1, and then below octant 2. So I'm going to bring them up here for you. There's octant 1. Octant 2 is back there. Do you agree with that? Does that make sense that it would be there? If we look at this from the top, that's what I was trying to say. If we get it back to look kind of like two-dimensional space, x, y, octant 1 is exactly where quadrant 1 is, except coming out at us. And then octant 3 is behind that one. Octant 4 is right above quadrant 4. Yeah? Do y'all see the 4 octants? And then the 5th octant is below the 1st octant. The 6th is below the 2nd. The 7th is over there below the 3rd. It's like a Rubik's Cube. And then there you go. There are your 8 octants. And we could go through and list all the qualifications for all 8 octants, but I think that's too much. So let's just pick one. Somebody pick one of these octants. I already did octant 1. Octant 7. Okay, tell me about, did I put Q a second ago? I put O, right? It was an O? Okay. Octant 7. Tell me about the X, Y, and Z in octant 7.
So
So I'm going to count myself around. 1, 2, 3, 4. That's 5, 6, 7's that back one, right? On the bottom behind. So what I'll do is I'll take all those other ones out of there so you don't. There it is, that back one. So the x coordinate is negative, the y coordinate is negative, and the z coordinate is negative. So they're all negative. Yeah? You could do that for all 8, but we won't. I have it built into this thing. If you just click on info, it'll show you what each octant, what the conditions are. All right, so now let's talk about some surfaces in R3. And we already discussed this. What would we get if x was 0? Tell me what that looks like in R3. Oh, wait, we didn't talk about this. We talked about R2, right? What is x equals 0 in R1? Point on a line, right? What's x equals 0 in R2? A line, which would be vertical, y-axis, right? In R3, what would this be? It's going to be, yes, it's going to be all points that look like this, right? Where y and z are free, aren't they? I can let y be free, go be free. Can you see? You just release it into the air. Be free. Do what you want. All right? Z is free. The only condition is that your x has to be fixed at 0. And that would force you to never come out. But you could let your y and z be anywhere else. So that's going to create that flat sheet of paper, that thing we just called the yz plane. There it is right there. And I'm going to bring it in real dark so you can see it. And I'm going to turn this. Right? Do you all see that clearly? That is x equals 0, which we will from now on refer to as the yz plane. And then if I let x be 1, that's going to move that whole plane, right, out towards us. So we're going to get another plane, but do you see there's that gap now, right? So you could say x equals 1 is a plane that is parallel to the yz plane, isn't it? It's just moved out one. Questions? What if I let y be 2? This would be a plane, right? Y is 2. Is a plane. It's parallel to what plane? What we are calling the xz plane. By the way, what's the equation for the xz plane? y0. Right? y0 draws the xz plane. X is 0 draws the yz plane. Z is 0 draws the xy plane. So see, there's 3 different coordinate planes that we have. Those are going to be very important to us, all right? Would you like to see just a glimpse into y? Just a glimpse? Okay. Because I know for some of you, probably no. right, let's see if you can see this. Okay, now I'm going to try and do my best to not blow you out of the water, but at the same time, make it curious enough for you to want to keep going on in this class. Back in Cal 1, if I gave you a polynomial function, something like x squared minus 3x minus 4, we know that this is a parabola, right? It's got 2x intercepts. Who cares? But that's what it would be, right? And we would know it has a minimum, right? Yes? The domain of this function would be what? Everything, right? Because it's polynomial. If we wanted to find like the area in here, yes, you would have to restrict the domain, and you could look at that area. Or I could say, hey, look, just between here and here, find me the biggest and smallest values, yes? That's kind of Cal 1 and Cal 2, the two different perspectives, yeah? But the idea is that you have a domain. And on that domain, which would be between here and here, you have a function, f, and you could be asked to find the max or min, right? Yes? That's perfectly okay in Cal 1? Now, what I want you to imagine is that this set of points right here, there's a bunch of points in there. I'm going to rotate it. I'm going to rotate it for you. Can you all see that three-dimensional, weird-looking solid? Can you all see it all right? Okay. Let's act like that's your domain. Every point in here is a domain point that you can plug into some function that's in a separate dimensional space. Okay, so you take a point from here, the point 4, 5, 7. You plug it into a function, it spits out a value. Okay? Every point in here you can do that with. What's the maximum of that function? What? So instead of having a domain that's just this little piece right here, your domain is a three-dimensional solid. How in the hell are we going to get our hands around a problem like that? Well, one of the first things we'll do is we will imagine projecting a light straight down on that solid. And when we do that, it's going to create a shadow on the ground, isn't it? And that shadow is being projected onto which plane? The xy plane. Yes? And then from there, we'll tear this problem apart and we'll be able to do it. All right? We'll chop it down piece by piece. But one of the key things is projecting that onto the xy plane. That's not the only way it could happen. There is a way that you could do the problem where instead of projecting this down to the xy plane, you could project it over to the, what would be that way? Xz plane, or you could do the yz plane. All right? So we have to understand where these planes are, you know, in reference later on. It's trivial. It's just one part of a bigger problem. All right. Sir? Okay. You, sir? You're not good. Your eyes are closed. That's not good with me. Okay. So what's the consequence, everyone? Sleeping in class? 10 points off your next test. All right, so that'll be the one warning for everyone. I'm totally serious about it. All right? All right, so get out of this. We okay with this general concept? You all right with that? We can move on? All right, so since we're in three-dimensional space, we may as well talk about trying to find the distance between 2 points, right? If we have 2 points in three-dimensional space, we can find their distance. We did it in two-dimensional space pretty easily, right? Someone gave you 2 points, x1, y1, x2, y2. We just connected that segment together, created a segment, and then we drew a right triangle, didn't we? Like this. And then we used the Pythagorean theorem. We could figure out that the distance between here and here would be x2 minus x1. Distance between here and here is y2 minus y1. And then if you set up Pythagorean on that, you can figure out this. How many of you remember seeing that? Anyone remember seeing that? Okay, if we extend that idea out to three-dimensional space, then we could take 2 points in 3D, draw a right triangle. Now that's difficult because we have to think about this. Let's say we pick 2 points in 3D. All right, so would you like to be a point today? Sure. All you have to do is hold that end. There's a point, right? And then here's another point in three-dimensional space. I'm going to draw a right triangle. But that right triangle has to run parallel to these 2 points. Does that make sense? Or maybe I could come this way and do it this way. Understand? There's only one, there's only one there's only one way to do the right triangle. I mean, you can rotate it around, but this change, this third dimension, allows for some variance, where on a flat sheet of paper, there's only one triangle you can draw. That kind of makes sense? Okay. So without us going through and solving it ourselves, I used to offer that as a bonus problem, but the problem is there's Google. So it's too easy of a bonus problem to come up with that formula. But as an exercise for yourself, it'd be interesting to see if you could come up with that formula on your own. Somebody gives you 2 points in three-dimensional space, x, y, z, and a second point, RST. The distance between these points is given by this formula right here. Does that formula kind of fall in line to what you'd already known about distance formulas for 2 points in 2D? It's the difference between the x coordinates, right? Squared, plus the difference between the y coordinates, squared, plus the difference between the z coordinates, squared. Add those all up, take the square root, that's the distance. So this animation allows you to just go through and change your x values and your first point's values and your second point, and then the computer will automatically calculate the distance. Let's see if we have an example here. No? Equation of a sphere. There's the equation of a sphere. I'll ask you to recall from Cal, or not from Cal, where did you talk about circles? Pre-Cal? Pre-Cal? Somewhere in the past, college algebra even. You may recall that for a circle with center HK and radius R, the formula in two-dimensional space was x minus h squared plus y minus k squared equals r squared. That look familiar to everyone? If the center of the circle is the origin, 0, 0, then this just becomes x squared plus y squared equals r squared. If we go to three-dimensional space, you still have x minus h squared plus y minus k squared, so that's all the same. But you now have this third component, this third piece. It's z minus, we're using L here, that's a lowercase l, squared equals r squared. And your center is now an ordered triple instead of an ordered pair. So there's our circle centered at, our sphere centered at the origin. I can move it around, right? Move it. Let's see, did I get it into the first octant? Kinda. So I'm going to ask you a few questions. We're not going to do them. We're not going to actually compute them. I just want to know if you could do these, because these are the types of things that you're going to be asked to do on homework. I'm not going to sit up here and do an example of every single type problem you're going to have on homework. If you understand the material, you'll be able to do the homework. If I give you this circle, I keep on saying circle, this sphere, I give you its center, right? Or I give you its equation, let's say. Then can you tell me the distance between the center of that sphere to the origin? Yes? You would just apply the distance formula, right? Okay. Could you tell me the distance between the center of the sphere and a coordinate plane, like the xy plane? So right now, I'm telling you, h is 5.5, k is 3.46, L is 3.04. Can you tell me the distance between the center of that sphere and the xy plane? What would it be? 3.04, right? Okay. And you could do that for the other coordinate planes if you wanted to. Coconut problem. Let's say I have a sphere that it's actually a ball, but the inside is hollowed out. So if we cut it and look at it from the inside, see it's hollowed out there? How could I describe this set of points to you mathematically? And what I need to do is tell you, let's just say that the outside radius is 8, and let's say the inside radius here is 5. How would I mathematically explain to you all the points that make up that coconut, that hollowed out ball? So would this be enough? By the way, it's centered at the origin. Would this be enough for me to say this? Or you should tell me, what does that draw? That draws the sphere, just the outer shell, right? What would draw the inside shell? But this would be what? 25. Right? That would draw the inside shell. How do I draw all the stuff in between? Well, we would have to draw every possible radius, wouldn't we? Like this, every possible radius between here and here. That would be impossible for us to write those all out. So what we're going to do is use an inequality instead. We're going to write this. The x squared plus y squared plus z squared, we know that it needs to be equal to 64 to draw the outside, right? But if I say less than or equal to 64, then it's going to draw the outside and everything down all the way to the origin, right? This is every radius from 8 down. But I don't want it to go all the way down to the origin, right? I want it to go to where? 5, so 25 here. Do you see what we've done is we've squeezed all the points between two different radii, right? Squared. We have to have squared there. That would represent all the ordered triples that would draw this coconut, yes? All right, now I'd like to venture into a homework problem. Just to give you a flavor for something that you're going to be asked. And this will also give you some idea of how what I say in lecture is not always going to just match exactly what you're going to see in homework. All right. Show this equation is a sphere. Find center and radius. Ready? Here we go. 3x squared plus 3y squared plus 3z squared equals 10 plus 6y plus 12z. You're texting too? My goodness, man. Seriously. You didn't watch the orientation at all? All right, well, I don't want to start on the wrong foot with you, but those are two things that cost you 10 points. All right. I'll give you a chance for redemption. If you can tell me how to do it. Anyone have any ideas? Complete the square?
Yeah.
Okay, so you're trying to get, if you can get back to this, right? If you can get back to that, right? If you can somehow turn this equation into this, you'll be able to identify h, k, and l, which will be the center, and you'll be able to identify what r is, right? So you need to somehow get some binomial expression in x squared, a binomial in y squared, and a binomial in z squared, yes? And the issue we have here is that in this equation, we do have x squared, but there's not an x over here. We have y squared, but there's a y over here. We have z squared, but there's a z over here, yes? So I'm going to bring everything to one side except the 10. And you are correct, sir. We are going to complete some squares here. Could we divide everything through by 3 just to kill off a factor of 3? We could, but except that would turn into a 10/3, but that's okay, right? I'm not going to. Now, the reason I'm not going to is because I want to make sure everyone here knows how to complete the square properly. So what is the technique for completing the square? You all remember? Let me try and break these up into 3 different groups here. This. We are going to complete the square on the x's. We're going to complete the square on the y's. We're going to complete the square on the z's. It's 3 different completings of the square. Now, on the first one, the 3x squared, we actually don't have to complete the square, because this one already looks like, kind of, this. This is 3x minus 0 squared, isn't it? So that's already looking like I can somehow turn it into this. This one, though, I can't because of that negative 6y. So what is the first thing you have to do before you complete the square on something? What do you have to have? Leading coefficient of 1 on the squared term. I don't have a leading coefficient of 1, I have a leading coefficient of 3. So I will factor 3 out like this. I've just pulled a 3 out of these 2 terms. Everyone agree I can do that? I'm going to do the same thing for the z terms. I'm going to pull a 3 on that one. I didn't pull the 3, did I? And I pulled the z. I don't know why I pulled the z. Minus 4z. Now I can complete the square. I can complete the square here and complete the square here. So once you have a coefficient of 1, what do? You take like, you half this thing, right? The number in front of the variable, right? You take half of it and then you square it, right? So half of negative 2 would be negative 1. Square it, which would be 1. And then what do you do with that 1? Okay, so I'm hearing all sorts of things. I want to know what the majority of you would do with that 1. Add it and subtract it immediately.
Multiply by 3 and then add it.
Multiply by 3 and then add to the other side. And then I heard add it to both sides. Those are the things I heard. So add and subtract it is correct. Multiply by 3 is correct. Add it to both sides is incorrect. And the reason why is because of this 3. So depending on how you learned it, you have to accommodate, you have to account for this 3. So the way that I've always taught completing the square is add and subtract it immediately. So that means you're going to write 3x minus 0 squared plus 3y squared minus 2y. And then why am I adding and subtracting it? What am I adding and subtracting? What was it, 1? 1 and subtracting 1. The reason why I don't do what you